So yours has something to look for. You're not it has. So like it, yeah. Like, Jason, maybe or like scrolling Should I start?
Yeah, I'm gonna.
Okay. Cool. Okay, so we're going to pick up where we left off last time, which was in the middle of the proof of the following proposition, which is that if delta and prime are membrane systems, for a tangle AT, then delta prime is jump equivalent to delta. Okay, and so just to remind ourselves of how the proof worked, we sort of started with two visions of the tangle. This is supposed to be two copies of the same tangle. And on the one hand, we have, under some parameterization, a nice view of the disk delta. And on the other view, we have a nice membrane system delta prime, intersection between. Okay. Something like this. All right, so then the first step of the proof one was that we can assume after isotopy that delta intersect delta prime contains no simple closed curves. Okay. And then, so this is, we did this last time, so I won't go through the details again. This was an innermost curve argument. And then step two, let's see, what did I say this was going to be? Well, step two, the goal of step two is to say that delta intersect delta prime contains no outermost arcs. Okay, and so I think the place where we were at with this was we had focused on some disk of delta, and we had another disk that was crashing through in an arc of intersection that was outermost and looked sort of like this. So. Common arc of intersection sort of lived in there. And the green guy bubbled out like this. And let's see. So we had realized that, so the case that we're interested in here is where we have an outermost arc of intersection in delta of this form. Right? Outermost meaning it co-bounds a little triangle, which meets the shadow of the orange disk and the tangle itself in two edges, and the third edge is the intersection. Okay. And so what we basically, I won't recreate all of the notation because it was a little bit wandering, but we saw that this triangle together with the green disk, which again we saw could have intersections with orange itself as well. So the triangle together with the green disk together with the sort of green semi-disk here on the bottom, which I think I call E, co-bounded or together gives a sphere, which must co-bound a ball. And so the idea is that we want to isotope the green disk to the triangle and then off to remove this outermost arc of intersection. And where we left off last time was the puzzle of what to do if sort of inside this ball, we see some arcs of the tangle. Okay. So let's see, what could the membrane systems for this portion of the tangle look like inside this ball? Well, the orange membrane system, delta prime, can be, the orange membrane system, delta, green is delta prime, can be fairly complicated, right? We can sort of have it doing things like this. Okay, so the membranes for those two arcs can come crashing out of that green guy because we made no assumption that in the green membrane system, we didn't make an assumption that this common arc of intersection be outermost. But we see outermost in the orange. So that means that the green membranes for these disks cannot escape this disk E. So I think I maybe was confused a little bit at the end, and I mentioned that they could go out this way. But of course, our assumption, which I didn't realize at the time, our assumption is that there are in fact no green membranes crashing through this triangle. Okay. So we don't really know quite what the green guys look like. Maybe they mess around in here a little bit, but we do know that they're sort of completely contained inside that green guy. So now what we'd like to do is we'd like to say we can take this green disk and push it off, but what we see is going to have to happen is we're going to have to do a number of jumps along these arcs as we go out. Okay. Okay. So maybe I'll just write this. We can isotope, but maybe I'll just, since this is new, I guess this disk was called delta prime. We can isotope delta prime to coincide with delta, but this involves jumping the disk delta prime. Well, it involves jumping the component of delta prime containing delta over any membrane of delta prime that intersects the interior of the disk E. So for example, this was our disk delta prime, but really we want to think of this as, sorry, this is actually, there's a way to make it a little bit more clear what's going on here. Maybe I'll try to do that. I have a decent picture in my notes. Yeah, well, maybe I'll draw it just a little bit different here. Just to give you an idea of exactly how this type of arc arises. We could have the shadow of our second membrane come out and then go in like this. This. Something like this, where it sort of wraps around and goes back through. This would then maybe completes something like that. So if you take the orange disk and you just sort of take a point and start, or maybe you take this, remove it, and drag it around, then you'll get this sort of arc of intersection back there like that. Okay. Well, I promised that that picture would be better than that one, but I'm not sure it is. Anyway, this disk here lying on the floor, I think was what we called E last time. Okay, so that is a quick return to where we were last time. Did I say the things I need to say? Is anything else need to be clarified, do you think? Any questions? So this allows us to remove outermost arcs of this kind. Of course, there might not be any outermost arcs of that kind. If, like we saw here, there was an outermost arc of the other kind sort of inside it. So I think maybe that it would be better for this to be step 3 in anything. And step 2, although really these steps can sort of be done. They're the same sort of idea, but I think it'd be better to actually focus on the other type of arc first. So step 2 is to suppose I don't remember what I was calling things. I suppose A is an outermost arc of the intersection delta, intersect delta prime, with the boundary of A contained squarely in the bridge sphere sigma. So the picture in this case is a little weird. Maybe it's even one more reason to start with this case. Orange shadow. And now we have an arc of intersection that looks like this. Okay, so we get this little disk delta prime, living in delta prime, and I guess our innermost disk here. Purple at some point is the disk delta, boundary A. And then we also get, in this case, the arc A shadow, which is sort of the segment of the shadow for this, this membrane, which intersects the semi-disk delta. And so everything goes more or less as before. Let's also call this systemic for E. So, again, similarly to the previous case, we have that delta union along, or union with delta prime, union E is a two-sphere, and there exists a three-ball, I guess we call this BQ. There's a three-ball BQ with boundary of BQ equal Q. And we can isotope delta prime to coincide with delta, then push it off using B sub Q. Okay. And again, when we do try to do this, we may encounter some green membranes in here, but we can push it off using BQ and jumping when necessary. Okay. All right, any questions? So that's pretty similar to the previous step. Well, this one's, which I should have done in the other order. This one's easier to visualize and describe, and can always be assumed to come in front of this one, whereas this one may not be, you may not be able to assume it comes first. Is that pretty clear? Now, let's see, are we finished? Are we finished? What do you guys think? Are we finished? So let's draw a picture of what things might look like. What have we arranged? Yeah, so sorry, what's the conclusion of steps 1 through 3?
No intersections.
No intersections. Delta intersect delta prime is I was going to say empty, but it's T. It's the tangle. So let's look at what this might look like. Okay. So we'll stick with the convention of sort of making the orange discs look nice. And then our green discs, well, we don't know quite what they do. Some of them could sort of do something like this. Okay. But some of them could do, in fact, let's make 2 of them do that. That's fine. Maybe a lot of them do that. But then some of them might do something a little bit more exotic, which in particular could look like this. Okay. So there's 2 membrane systems for this trivial tangle, which don't intersect away from the tangle, but are not yet isotopic. But okay, so what's the step look like here? Well, so for each strand, strand E of the tangle, let what do I call the little discs, the individual discs? I guess I indexed them. Let's stick to the notation here. Let's let delta and delta prime and delta prime be membranes for that strand T. So you might think of this delta and this delta prime, or you might think of that delta and that delta prime. Okay. And so again, it's actually a similar flavor yet again. So we have shadows, right? We have shadows. I guess we have a shadow T star and a shadow T star prime coming from each of these membranes. So this would be T star prime, and this would be T star. Maybe we're going to concentrate on this case. And so we have that T star union T star prime equals C is a closed curve, a simple closed curve. It's a simple closed curve, and it's embedded in sigma. If we take out the tangle accepting the one we're interested in, then the curve is embedded in sigma. And so there exists a disk E now the disk lies in sigma. The disk lies in sigma, such that the boundary of E is T star union T star prime. And so this is this disk here. And so now what we can do is we can use, so that means there exists a 3-ball BQ with boundary of BQ equals sphere Q, which is given by E union delta prime. And we can use this ball to isotope the disks to coincide. So we use BQ to make delta and delta prime coincide, jumping if necessary. So if this were our BQ, right, this was our little E, that was our BQ, we wouldn't have to jump, but in this case we do have to jump. Okay, and that's the proof. Any questions? All right, so where do we go from here? Let's see. So this was sort of a flashback. This proposition was stated a while ago, and I postponed the proof, but now we finished it, so we can reconvene wherever we were previously in the lecture notes. Any general questions or anything? So about the notion of reducibility for a bridge splitting. Okay. So B, I guess we'll just call it C for now. Simple closed curve C. That bounds trying to find what is. Okay. What does it? All right. Sorry. I guess it's not really that. It's not that big. Sorry. Let me Command Z and replace what I just did. That's what I did. There exists an essential C in sigma minus such that C equals the boundary of D1 and also equals the boundary of D2 for properly embedded disks by minus D sub I. Okay. And then, yeah, just to be clear, what do I mean by essential? Essential here means that C does not equal the boundary of D for any disk E living inside the bridge sphere minus the bridge points. So it's not a null homotopic curve inside that function sphere. Okay, so what an example is something like this. I have something like this. We have a trefoil over here. On bottoms. And the curve I would be interested in would here. C. And the disks that we would see that it bounds would be a disk above, so this would be D1. And this implies that there exists a sphere, Q, in S3 minus the link exterior, such that Q intersects sigma equals a single curve C. Okay. So Q is what we call a reducing sphere or a splitting sphere. Okay, so let's introduce. Let's call this sphere. So maybe by reducing sphere now we'll particularly mean that a central sphere in the exterior that intersects the bridge surface sigma in a single curve. Oh, and then I guess I should also say that C is called a reducing curve. So reducing curves and reducing spheres are obviously in one-to-one correspondence. They're the same thing. This definition. Okay, so when do reducing curves and spheres? Well, we have this nice theorem of separates the components of. So there exists a splitting sphere S3 minus L. Okay. What this theorem is not saying is that Q can necessarily be isotoped to be a reducing sphere. Okay, so the output of the theorem, so the hypothesis of the theorem gives us this. The theorem gives us that there exists a reducing sphere Q prime in S3 minus neighborhood of L. And so this Q prime a priori could depend on the bridge splitting and so I think this actually raises a question that I don't know the answer to, which is the following. So the question, well, it's the thing that you think that this might be saying before you realize it's not saying that. Okay. So questions in this course, I think, are things that I don't know the answer to, or at least that I don't remember knowing the answer to. Other things that I think I know the answer to will maybe be exercises. Okay. We'll see if I can stick to that. Okay, yeah. So the question, the natural question is, given a split link is every reducing sphere, is every splitting sphere isotopic to a reducing sphere? In other words, can any splitting sphere be isotoped to intersect the surface in a single curve? So the methods of this proof, maybe I'll just tell you a little bit, kind of the extent to which I investigated this. So let's suppose our split link looks something like this. I'm not leaving myself a lot of room for this drawing, but I get the idea. So what might a complicated sort of splitting sphere look like in this case? Well, let's have it crash through there and here. And so it kind of comes down. So it's going to intersect the bottom angle, the bottom three ball in nice cases. But then when it comes up here, it sort of begins misbehaving. Get to that part of the board that doesn't tie it very well. Starts tying itself in a knot. Maybe does something like this before coming back down. Okay. So this is a splitting sphere, which at first glance is not necessarily isotopic to a reducing sphere. And I'll just tell you the way that Nagami and Okita deal with a case like this is the first thing they do is they look at essential curves. Let me try that one, it'll show up better. Maybe here. They look at these sort of essential curves. If you cut the sphere into two pieces, the top part and the bottom part, they look at essential curves in each piece, meaning the curves that bound a disk in that piece, but do bound a disk in the exterior of the piece, and then they cut along. To throw it away. But what they would do in this case is they cut this thing open, two spheres, and they're actually both reducing spheres because they found this guy, for example, here. Now, what do you think? Was this original sphere Q isotopic to a reducing sphere? Doubt it. I didn't think so at first because I was trying to come up with a counterexample, but I think it actually is. I mean, I think you can pull this down and around there, maybe. Yeah, I think you could just kind of pull this down and around, and then back up to undo one of the crossings.
But you said isotopic and the complement, right?
Yeah, complement of the link, yes. Just a complement of the bridge. But yeah, sorry, maybe it's not super clear what I'm saying to do. I'm saying like take this bit of the surface that runs here, and sort of drag it down. So it'll crash through here, and then it'll kind of come around like that. It'll crash through there also. But then you sort of down there. That's where it was. Its crossing is reversed. And then it's not nearly as intimidating with only one crossing. And then yeah, because once you've done that, then I think you can. And I don't know. So that's why it's a question. And I think this is a
Think of the sphere as a bunch of randomly embedded spheres union neighborhoods of arcs, and you somehow want to do some crossing chain among these arcs by the operation you described.
Oh, do you want like the balls in arcs? Yeah.
I don't know. I mean, if it's true, sounds like things should work.
Yeah, if it probably is, and this sort of thing shows up repeatedly in this series. If I were going to simplify it the way I described, I first have to make my intersections with the bridge sphere more complicated. And this is always sort of very intimidating. Okay. Not being able to sort of monotonically decrease complexity like we did in this example.
The curve is just a curve, it's not a union of curves or
Just a curve.
just a curve.
Yeah. What did I call it?
No, it's, yeah.
An essential curve. Yeah. Simple closed curve. That's right. Okay.
So in this paper, they get the reducing sphere by always surgery of the splitting sphere.
Yeah, maybe not always, but at least in a priori, sometimes they do need to do a surgery, which splits the splitting sphere into other spheres, and then they throw one of them away and repeat. Yeah. So we talked about this a little bit, like when we were doing the innermost curve argument in this proof, right? When we had this like innermost curve of intersection, one option would be just to cut it, to serger. The sort of balls that this cuts, it's actually a split link, so it's highly reducible. Irreducible. Complement is not irreducible.
What are we reducing here? what are we reducing here? I mean, we call them like reducing sphere with this union of two disks.
What are we using for curve intersection?
But do we use it to?
No, it's just, well, we can prove the following corollary, which is a nice corollary. This ends up being useful. So every B bridge splitting of the N component unlink is unlinked with B greater is perturbed. And so, I mean, the idea here is we know that the unlink, because it's a split link, a reducing sphere, and we can sort of repeat inside that reducing sphere, we can repeat the argument, or it's stabilized, right? So we know that sort of in here we find these disks which intersect in a single and perform a deperturbation. Okay. And so this tells us we can do, and so by repeating, we can do it to each component of the unlink until you know, if it doesn't have bridge number n, then it must be a perturbation. Okay. Okay. Yeah, so somehow knowing that the existence of a reducing sphere is a nice kind of thing to be able to pull yourself up with when you're trying to prove things like this. Okay, so this gives us an exercise and a question. So the exercise is, I think this is an easy exercise. How many distinct B bridge splittings does the N component unlink have? Okay, this is an easy exercise, I think, but it's actually ends up being, I think this has important relevance to bridge trisections. Okay, and then the question, which I'll try to motivate. So again, questions are hard. How many distinct reducing curves can a bridge split? How many distinct reducing curves can a bridge splitting of use of N unlink? And I'll tell you what I mean. There might be a question of how well defined this question is at some point, but there are at least some interesting cases hiding somewhere in here. Okay, let me try to draw a big picture. What's the big picture? Okay, this example is due to Alice. And this threw a wrench into something we were trying to prove, which is always fun. Okay, so there's a trivial tangle above. The trivial tangle below